Hey guys, welcome back. This video, we're gonna talk about delta time. What delta time is, why we need delta time, how to calculate delta time, and how to use delta time. This video is gonna be in roughly 3 parts. The first part is gonna be a simple demo that we're gonna create to visualize why we need delta time. The next part is gonna be calculating the delta time. And the final part is gonna be using delta time and fixing our problem. So let's get started. Like I said, first we need to create a simple demo to visualize the problem. This whole delta time thing will make more sense if this is the first time you hear about it, the more we continue. So hang in there, and by the end of this, hopefully you'll have a good idea of what delta time is and how to use it. Okay, so let's take a look at our code here. What I want to do is basically draw a simple rectangle to the screen and have the rectangle move from the left side to the right side. To draw the rectangle, we're going to do it inside of these two lines here. So here we're clearing the screen and here we're presenting to the screen. And in between those, we're going to do our rendering. So we always want to do our rendering after we clear the screen. That's the right way to do it. And to draw a rectangle, we're going to use a call called fill frect. Fill rect f. Okay, so SDL render fill rect f. Let's copy this. And as you can see from the description, fill a rectangle on the current rendering target with the drawing colors at sub-pixel precision. And the sub-pixel part is important. I'll get back to that in a moment. Well, let's try and oops, I didn't copy it. Let's try and pasting this. It takes in the renderer, which we call the global renderer, and then it takes in a pointer to an SDL frect. So let's quickly talk about SDL rect and SDL frect. So SDL rect is a simple structure that represents a rectangle. It has an X and Y position and also has a width and a height. So the X and Y fields here represent the upper left corner of the rectangle, and the width and the height basically define how big the rectangle is. This is fine, but it's using integers. So with this, we can't really represent values in between pixels. So if, let's say, the start of the rectangle is somewhere between the pixel 1 and pixel 2, we can't represent it with this one. So what we're going to do is we're going to use SDL frect, which actually uses floats instead of integers. Otherwise, it's exactly the same. It has its own functions, as you saw, like this SDL render fill rect f takes in a SDL frect instead of an SDL rect. You'd need to use SDL render fill rect without the f if you wanted to use an SDL rect, basically. Okay, so let's define an SDL frect, and let's define it outside of the main function here because we want this to persist in between frames. And I'm just going to call this test rect because it's just going to be for testing purposes. So like I said, this is going to define our rectangle. So let's have the rectangle start at 0 in the x-axis. Remember, this is going to be the top left. So let's have the y value at the center of the screen, which is going to be the global screen dim.height divided by 2. And we also need to subtract half the height from this to position it exactly at the center. But first, let's define the width and the height. I'm going to make this a square, so let's just say 50 and 50. And like I said, let's subtract 25 from this to have it exactly on the center. Now I'm just going to pass this test rect to SDL render fill rect f. And I'm going to try to compile and run this. And you will quickly see that this doesn't do anything. We still have a blank screen. And the problem here is we're still drawing with the same gray that we set before we started the main game loop. So here we're setting the render color to be this gray. but we're never changing it. So what we need to do is, right before we render this rectangle, we need to set the color to a different color. So let's set this to be a green. Red, I'm sorry. But now, as you can see, it's all red. And the problem again here is we're setting it to red here. And the next time we go through the loop, it's still red. And now we're clearing the screen to red. So what we need to do is, before we clear, let's set it to that gray again. And after we clear, just before we draw the rectangle, let's set it to red. So this time it should work properly and we should get a rectangle at the left side of the screen. And as you can see, the top left of the rectangle is at the center on the height, on the y-axis, and on the x, we're at 0. Great. And the reason this gray, like the one that we set up here, didn't work, and we have to do it again here because this one is outside the main game loop. So this is just called once, but everything in here, everything inside this while global running is called again and again. Okay, great. So now we have our rectangle being displayed. So like I said, the next thing I want to do is have it move from the left edge to the right edge. So to do that, it's very easy. We have the test rect here. We're just gonna increment its x position by, let's say, 2. Every frame. Remember, this loop is being called again and again and again. So every frame, we're gonna say, move this rectangle 2 pixels to the right. And as you can see, the rectangle is moving towards the right side of the screen. It's moving at a nice slow pace. And the reason it's moving to the right is because we're adding 2. So it's going in the positive direction and it starts from 0. So the left side of the screen is 0. So we're going in the positive x. That's why it's going in the right. Okay, great. So that's basically the first part of this video, getting the demo ready. And now we can start talking about the main topic of this lecture, which is delta time. So what is delta time? So delta time is basically how much time that has passed since the last frame. So here we're starting the frame right at the top of the main game loop. And down here we're ending the frame, right? So the amount of time that has passed since the start of the frame until the end of the frame is delta time. So that's delta time in a nutshell. And I'm actually gonna demonstrate a major flaw in the way we're doing things right now. Here we're saying, okay, add 2 to the position of the rectangle each frame. So right now we have vsync enabled. So that means we're running at 60 frames per second for my machine right here. So that means each frame we're adding 2. So let's open up our calculator here. So each frame we're adding 2 to the position and we have 60 frames per second. So that means we're moving this rectangle at 120 pixels per second. And that's all fine. And if everyone who ever run the game had the same FPS, it would be just fine. But reality isn't that perfect and different people have different computers with different speeds. So if someone runs the game at a different frame rate, this code will actually have a different result. Let's say someone is running this game at 30 frames per second. So we're still moving 2 pixels each frame, but now we have 30 frames per second. So the same code, 30 frames per second, will move the rectangle 60 pixels instead of 120 pixels. So the result will be half as fast. And that will lead to different results in different machines, like I said. So one player will see the rectangle moving at a much slower speed. So if that was our ball in our Pong game, the game would be half as slow, like I said. We don't want that. We want the game to be the same speed. We want everything to be the same on every machine, basically. And this is where delta time comes in and saves the day. Like I said, delta time is the time that has passed since the last frame. And we can use that value and we can multiply this value, the 2 we have here, to get the same amount of value to increment the position every time. But we first need to change the way we think about this distance that we're setting here. Right now, we're thinking in terms of move 2 pixels each frame. We need to switch to thinking in terms of, okay, I want to move 120 pixels in 1 second. So we're going to say, I want to move 120 pixels in 1 second. And the way we make sure that's correct is by multiplying this by delta time. We don't have this delta time value yet, but this is how we're going to use it. And like I said, that delta time is going to be, if you're running at 60 frames per second, that's going to be 1 over 60. If you're running at 30 frames per second, that's going to be 1 over 30. And if you're running at, let's say, 2 frames per second, which is an extreme case, that's going to be 1 over 2. So imagine we're running at 60 frames per second. If we multiply 120 by 1 over 60, that's going to be 2. So at 60 frames per second, each frame we're adding 2. And that adds up to 120. With 30 frames per second, each frame, if you multiply 1 over 30 with 120, is 4. So each frame we're moving this by 4. So as the frame rate goes down, the distance that we move this rectangle will increase because we have less frames. So this delta time value will make sure that we're moving the same distance with different frame rates. And before we actually calculate this, let me quickly show you. If you go back to the 2 here, if I run the game now, you can see that it's moving at a nice slow pace because we're running at 60 frames per second. But watch what happens when I get rid of the VSync flag here. Let's take this out. And as you saw, the rectangle just flew past the right side of the screen because the frame rate is really high right now because we have a very bare bones game. So the frame rate is very high. And like I said, this line here that increments the position is being called again and again, much more than 60 frames per second. So the code is the same. I can literally just add the flag again and it will slow down again. So the code is exactly the same. The only difference is this is just being called at different rates. So that's just the demonstration of the problem so that you can see why we need delta time. And now let's get to calculating the delta time value. To calculate delta time, we're going to use 2 very useful calls from the SDL library. Let's take a look at the wiki. And those 2 calls are called SDL get performance counter and SDL get performance frequency. These use what is called the high resolution counter that is on the CPU, which is basically a counter. You can think of it as like a clock that counts the amount of time that has passed. And this get performance frequency call returns, if I'm not mistaken, here it says get the count per second of the high resolution counter. So it's the count per second of the high resolution counter. So the high resolution counter is counting, and this is the amount of times it counts in 1 second. So we're just going to use this value, which is going to be a very high value, like 1 million, 10 million, I don't know exactly what it is. We're just going to use this to convert what we get from this call, which is called get performance counter. And this just returns the value of the high resolution counter. So you can just think of it as asking the time. You look at the time, oh, it's 10 o'clock, and you look at like 30 seconds later, oh, now it's like 10 o'clock, but 30 seconds passed. And we're just going to use this to time how much time it takes to go through a frame. And these actually line up exactly with the native calls of, for example, the Win32 library. I actually have some bookmarks here that I want to show you guys. And look, this is the MSDN documentation for the Win32 library, which is the Windows's, library to do stuff. And here we have query performance frequency. which is exactly this one. And then we have a query performance counter, which is basically same as this one. And I would be amazed if this doesn't just call this one. You know, it's probably like under the hood SDL is just calling this function here. So if you want to learn more about this, you can go read these. I might have these on the description. There's also this very useful article here that you can read. It's about acquiring high resolution timestamps. I'm not going to go into these, but if you want to learn more, these are very useful. Okay, so let's start using these actually. But before we use them, I actually want to change something real quick. From this function declaration, you can see that it's returning a uint64, which is an unsigned integer that is 64 bits. And look at the way that this is written. It doesn't say unsigned space integer and or like unsigned space long integer or something like that to make sure that it's 64 bits. It just says uint64. We want to do a similar thing. And there's actually a standard way of doing this, which is using a header called stdint, which I'm gonna include here. It's called stdint.h, and let's do a quick search for this. And it's this one here. And this basically defines some types for us that are guaranteed to be a certain size. For example, here you can see that there's a type called int32_t. So this is a signed 32-bit integer, and this is guaranteed to be 32 bits. Because if you just use the plain old int, it might have a different size depending on the machine. It might be 16 bits, 32 bits, who knows, right? So if you want to make sure that you're getting the exact size you want, you need to use these types. So in this case, we want an unsigned 64-bit integer, so we would use this uint64t type here, but I'm actually gonna go one more step beyond that to make it even more convenient to use, because I don't like these names. They're a bit long. They have this _t after them, which is painful to type, cumbersome to type. So I have my own type defs here that I use. So I'm just gonna copy these and I'm just gonna paste these into my application here. And these just line up to the same ones. Let's actually get this here. Like, these are the same ones from the stdint header, but I'm just type defing them into even shorter names. Like, signed integers are prefixed with s and then the size of the variable. Like, this is an 8-bit signed integer, s8, s16, s32, so on and so forth. And for unsigned integers, I just have u and the size, like u8, u16. This is much easier to type, much easier to use. In my experience, you're not forced to do this. You don't need to do this. You know, you don't even need to use the standard int header here. You can just use the normal ones. I also have float and double type def to f32 and f64 here as well. And finally, I also have this b32 because I usually don't use the Boolean type that C++ provides. I just use a signed Boolean, signed integer, which works the same way, actually. There's not much difference there. Okay, so great. I wanted to do that. And lastly, I also want to take this stuff and actually create a header file here called stdl.pong.h and move the stuff there because it's getting a bit crowded here. So let's copy these guys. And let's actually create stdl.pong.h. Let's put this stuff here. Okay, great. And like I said, let's start using, let's start using these type defs. So here, instead of this bool, I'm gonna switch this to b32. And what else? We have some integers here. These are gonna be signed 32. And let's see. Everything seems good here. Let's go to the main file. We have unsigned integers here. These are going to be u32s. Unsigned integer here as well. What else? Let's look. Let's see. That seems to be all, actually. Okay, that wasn't so bad. We can leave these here as the default ones. That's fine. So, okay, enough with that tangent. So, like I said, we want to use this first, the get performance frequency. It returns an unsigned integer, 64 bits. Let's copy this. And before we enter the main loop, let's create an unsigned 64. And we're gonna call this perf frequency. And that's gonna be that. We can actually take a look at this. Let's try to compile. Let's get into our debugger, and we're gonna set a breakpoint here, and we're gonna try to see what the perf frequency is. Let's run the game. And as you can see, it is 10 million. So the perf frequency is 10 million, which means the count per second of the high resolution counter is 10 million. So it does 10 million counts per second. And again, we're just gonna use this value to normalize the values, not normalize, but make these values a bit more readable. So now let's actually do the calculation of the delta time. We're gonna use this call first to create the FPS counter here. And that is going to be the result of get performance counter. We can also quickly take a look at what that returns. It's not gonna make sense now, actually. So this is really not a good idea, but so as you can see, it's some crazy value, crazy large value, but this is actually going to, when we call this again, it's gonna give us a more increased value. Then we're gonna do a subtraction. You'll see in just a moment. Okay, so we have these two here, which is all we need before we enter the game. And at the end here, after we do all the stuff that we need to do, we're gonna have a section called delta time. And in here, we're gonna calculate the delta time. So at the end of the frame, let's do another call to the performance counter, another U64. This is going to be the end counter. It's the end of the frame. And this is also going to be a call to performance counter. So this is also going to give us a time value. So now we have the time before we entered the main loop. So effectively the start of the frame, the first frame here, the FPS counter. And then we have the time value at the end of the frame. So the only thing we need to do now is just to subtract them from each other. And that's going to be the elapsed time. How much time has elapsed? And that's going to be the end counter minus the FPS counter. And even this will actually give us a more sensible value, actually. So let's do an SDL log. Let's say elapsed. That's going to be, I think, an LLD. Elapsed time. And finally, we actually need to set the FPS counter to be the end counter, so that FPS counter always has the right value, which is the time the next frame starts. Here it looks like it's the end of the frame, but it's actually the start of the frame because it's after everything is over and after we make the FPS calculation. Let's compile that. Let's try running this. And as you can see, we're getting a smaller value now because it's the difference between the FPS counter and the end counter. But still it doesn't make much sense to us, right? What is it? It's like 160,000 something, 170,000 something. Doesn't make much sense to us yet. So what we need to do now is use that performance frequency value to make this into a more understandable value. So we're gonna take the elapsed time and we're gonna divide it by the perf frequency. And we actually need to cast these to be floats first because they're gonna have a decimal value. Okay, let's try this again. So that's not going, yeah, that's still going to be the elapsed time, I guess. That's fine. And now, as you can see, we're getting a crazy value because I just forgot to change this from an LLD to an F, because now it's a floating point value. Okay, great. Now we're getting something more sensible. So as you can see, it's like 0.016171159. So at the start of the series, not the series, the lecture, I told you that, for example, if we're running at 60 frames per second, our delta time is going to be 1/60. If you check what 1/60 is, it's 0.01666666, which is exactly what we're getting here. It's not exactly the same, but as you can see, it's pretty close. It's actually the exact same value here. It's pretty close. And what I'm saying is that this is actually the value we need. We actually calculated the delta time. So this calculation here is the delta time. Okay, so did we create a variable for the delta time? Not yet. Okay, great. So let's create a delta time value. I'm going to take this variable up here. And let's say it's going to be an F32, a float 32, which is just a float. If you look at our type defs here. And we're going to call this global delta time. I'm going to make this a global because we're going to want to use this from a bunch of different places. Let's go back into our game. And instead of just printing this, let's cut this and let's say global delta time is this value. And let's comment that out. So now we have the delta time. So we can actually fix the problem that I was talking about, the problem of having different speeds at different frame rates. So now we're gonna use the delta time here. And like I said, we're gonna stop thinking in terms of how much to move each frame, and we're gonna switch to thinking about how much we want to move per second. So we want to move 120 pixels per second, and that should be good. That should be what we got at the start of the lecture. But now, the crucial point, let's try turning VSync off. So as you remember, when we first did this, the rectangle just flew away. But this time, hopefully, we're gonna have the exact same result because we're using the correct delta time. And let's actually print those values for debugging purposes. We're not going to have these in the final game, obviously, but let's say, well, let's first print the FPS. And the FPS is a bit different. Right now we have the milliseconds each frame takes, which is the delta time. The FPS is actually a very similar calculation. It's going to be the performance frequency divided by the elapsed time. So it's reverse, basically. That's going to be the FPS, and let's also print the milliseconds per frame. And that is going to be the delta time. But let's actually multiply this by 1,000 because delta time is in seconds right now. In order to get the milliseconds, we're gonna multiply it by 1,000. Let's compile. Let's run the app. And it's going crazy because I probably did something wrong. FPS looks totally crazy. Okay, let's try turning VSync on for a second here. And actually the FPS is fine. I guess we just had a crazy high FPS, so it looked wrong to me. I thought that was a bug. But as you can see with VSync on, we're getting roughly 60 frames per second, and milliseconds per frame is about 16, which is good. That's the value we want. Let's turn it off again. Let's see how much FPS we're getting then. Whoa, okay. So actually, yeah, I guess that's fine. We're getting about 2,000 frames per second, which is okay. So yeah, this is working. As you saw, it's not perfect. So with 60 frames per second, it's not always 60. the FPS. Also, the millisecond isn't always perfect. We can actually go a couple more steps further and really get this bulletproof and really make sure we're getting the same amount of time each frame. But I'm not going to do that now because that's going to take like 3 times more time, and it's really not that going to be useful to us in the short term. We might do something like that after we build some parts of the game. But yeah, this is roughly the delta time calculations that we're going to do. So we talked about why we need delta time, what is delta time, how to use delta time, how to calculate delta time, then how to use delta time. This has been a long one. Delta time is always complicated. To do this type of stuff is always complicated. I'm not the best at it. I don't exactly know how all of this works to a T, but I just know how to get it running and get it set up. In the next one, we're probably going to start building the actual game, at least the systems of the game. Up until now, it's been mainly low-level stuff, engine work, one might say, even though this is a teeny tiny game. Not going to be much of an engine underneath it, but still, it's low-level stuff. It's the bare bones things that we need to write before getting to our game. But like I said, hopefully in the next couple of lectures, in the next few lectures, we're going to dive into the game. Like I said, if this didn't make sense initially, try reading about it a little bit on the internet, maybe try watching this video again. And I will see you in the next one.